right, class, so today we're going to be going over the exam review for test 3, and that covers chapters 9 and 10. So, for the first problem, I want you to tell me whether you're going to be using a normal distribution, that's when you find a z-score. A t-distribution, that's when our standard deviation is unknown. A chi-squared distribution, that's when we're comparing two variables and whether or not there's a relationship between those two variables. Or ANOVA testing, which is when we're looking at whether the means of multiple samples are the same or different. So, for this first example, we're looking at the health of the bear population in Yellowstone National Park. And it's monitored by measurements taken from anesthetized bears. So assuming the population standard deviation is known, right, that is a key piece of information. We're going to test the claim that the population mean of all Yellowstone bears is greater than 150 pounds. So, because we know our standard deviation, that's when we're going to use a normal distribution, so our sigma is known. So we're going to use a normal distribution. Next, let's take a look at example, part B. A study commissioned by the U.S. Department of Education based on responses from 1,015 randomly selected teenagers test the claim that fewer than half of all teenagers in the population feel that grades are their greatest source of pressure. Okay. So let's take a look at this. Now this doesn't give me a standard deviation. It also doesn't give me a mean. The reason it doesn't give me a mean is because this is going to be a test of proportions, right? Fewer than half, right? So our null hypothesis would have been p equals 50, and our alternate hypothesis would be p is less than 0.50. And when we're working with proportions, the only test we can use that we know of at this time that we're going to use in this course is a normal distribution. So we're going to go ahead and find our z-score because we're working with proportions. Okay, for C, when birth weights were recorded for a simple random sample of male babies born to mothers taking a special vitamin supplement, the sample mean and sample standard deviation were found. The birth weights for all babies are assumed to be normally distributed. That's something we need. So we're going to test the claim that the mean birth weight for all male babies of mothers taking the vitamin supplement is different than 3.39 kilograms, which is the mean for the population of all males. So we have a sample mean, we have a population mean. What we're given that's different, though, is a sample standard deviation. Because we do not know our population standard deviation, this is when we're going to use a t-distribution, also called a student's t-test. So we're going to use a t-distribution. All right, for D, a simple random sample of subjects was obtained and each was tested for left-handed writing. Test the claim that whether a person writes with the left or right hand, with the left hand is independent of gender. So here are two variables that we're comparing. We're comparing left-handedness and gender. I don't think I've ever met a left-handed girl. I definitely know quite a few guys who are left-handed, including my grandpa. So we're comparing these two variables, and when we're comparing two variables, that's when we're going to use a chi-squared test. A chi-squared distribution also can be written as chi-square, depending upon your writing preference. Okay, last but not least, for E, a researcher obtains random samples of SAT scores from students at 3 different colleges. We want to test the claim that the mean SAT scores at each college are different. So this is when we're going to be doing an ANOVA testing, right? That's because I want us to think about the fact that our null hypothesis is that all the means are the same, and that our alternate hypothesis, so this is our 3 universities, is that at least one of the means is different, so they're not all equal. So we'd be doing an ANOVA test on this example. All right, So for problem 2, a simple random sample of 50 adults, that's going to be our sample size, is obtained, and each person's red blood cell count is measured. The sample mean, that's our X bar, is 5.23 cells per milliliter. The population standard deviation for red blood cell count is 0.54, so that's our sigma. I want to test the claim that the sample is from a population with a mean less than 5.4 cells per milliliter. So, that's the value often used for the upper limit for the range of normal values. So, let's state our null and alternate hypothesis. We're going to figure out what type of test this is, find the z-score, find the p-score, and then state our conclusions at the 0.05 and the 0.01 significance level. So I'm going to go to a blank page. So what's my null hypothesis? Okay. My null hypothesis is that my mean equals 5.4 cells per milliliter, right? It's no different than the given value. My alternate hypothesis is that my mean is less than, that's part A, 5.4 cells per milliliter. This is going to be a left-tailed, oh my gosh, Bobby. This is going to be a left-tailed test, right? Because if we were to draw a normal distribution with our mean, oh my gosh, you guys. Bobby, I will play with you as soon as I am done. So with a mean of 5.4, our value that we found for our sample was 5.23. So I'm trying to find the area in this tail right here. Okay, I'm trying to find the area right there. So I'm going to need to calculate my z-score. Okay, remember that our area under this curve, what's in orange, that's going to be the same as our p-value. So let's calculate our z-score. I have z equals my sample mean minus my population mean over my standard deviation divided by the square root of n. So that's going to be 5.23 minus 5.4 over 0.54, that was our standard deviation, over the square root of our sample size of patients, which was 50. That's going to give me negative 2.23. So that tells me that 5.23 is negative 2.23 standard deviations away from the mean. So what I need to do next is look this up in a z-table. The z-table is going to give me the area to the left of 5.23. So if I go to a z-table, I find an area of 0.0129. Okay, that's also my p-value. So for part D, we're going to have a p-value of 0.0129. So I'm going to examine this at the 0.05 significance level and the 0.01 significance level. Remember, we want our p-value for this left-tailed, we want our p-value to always be less than our significance level. So at the 0.05 significance level, 0.0129 is less than 0.05, so we can reject our null hypothesis at the 0.05 significance level. For part F, which I'm going to have to write over here, guys, it won't let me write below this line, we're going to examine it at the 0.01 significance level. So at the 0.01 significance level, is my p-value less than 0.01? No, okay? 0.01 is not less than, sorry, 0.0129 is not less than 0.01. So we do not reject H naught at the 0.01 significance level. Okay, so those are our steps. Let's take a look at another example where we're looking at the distribution of sample means for hypothesis testing. So, a simple random sample, this is actually problem 3. A simple random sample of 50 adults is, oh, this is the same question. Let's try this again. This is sample 3. Okay, this is problem 3. In a study of 1,228 randomly selected medical malpractice lawsuits, it was found that 856 of them were dropped or dismissed. I want to test the claim that over 50% of medical malpractice lawsuits are dropped or dismissed. So in this case, we're going to be looking with proportions. So I know that my population proportion is 0.50, and I need to find my sample proportion of cases that were dropped or dismissed. So I had 856 out of 1,228. That gives me, I'm going to round this to 0.70. So, and my sample size is 1,228. That's all the information I am given. So I'm going to go ahead and I'm going to state my null and alternate hypothesis. So my null hypothesis is that P equals 0.50, right? Our null hypothesis always has an equal sign. There's no difference from the claimed value. My alternate hypothesis is that P is greater than 0.50, because the claim that over 50% of cases were dismissed. So I have P is greater than 0.50. So what type of test is this? Is it left-tailed? Is it right-tailed? Is it two-tailed? This is going to be right-tailed. Okay, so if I was to sketch this out, my proportion, population proportion's right here. I've got 0.70 right here. So I'm trying to find the area in this tail. So I want to find the z-score for this sample proportion. So the equation for z-score, probably not want to write this with a highlighter. The equation for our z-score is p hat minus p over the square root of p times 1 minus p over n. And remember that these equations to calculate the z-scores are going to be given to you. You just need to know when and how to use them. This gives me 0.70 minus 0.50 over the square root of 0.50 times 1 minus 0.50 over this 1,228. This gives me quite a big number, right? 14.28. Okay? Now remember from our 68, 95, 99.7 rule that 99.7% of the data is within 3 standard deviations of the mean. This is really far away. So if I look this up in a z-table, I will get 0.999. That's really close to 1, right? But it's not perfectly 1. In order to find the area in this tail, I need to take 1 minus 0.999. That gives me 0.001. This is my p-value. So I have my p-value is 0.001. So we would reject the null hypothesis at the, do I want to use the 0.05 or the 0.01 significance level? Well, 0.01 is less than 0.05. Sorry, 0.001 is less than 0.05, but it's also less than 0.01, and we want to use the smallest one we possibly can. So I'm going to reject H naught at the 0.01 significance level. Okay guys, let's take a look at problem 4. So a study was conducted to estimate hospital costs for accident victims who wore seatbelts. 20 randomly selected cases have a distribution that appears to be approximately normal with a mean so this is our sample mean, of 9,004 and a standard deviation of 5,629. That's our sample standard deviation. So in this class, we're going to be constructing a confidence interval. When we're working with confidence intervals, we're always going to want to use the area in two tails. And it's important to note that we can only construct a 95% confidence interval using t-values, right? We can't construct a 90% confidence interval or a 99% confidence interval because the area that we're given in either one or two tails is always going to be 0.05. Okay, so how do I determine the critical value of t? Well, I know I need the area in two tails. Next, I need to know my degrees of freedom. So my degrees of freedom is my sample size minus 1. So in this case, my degrees of freedom is 20 minus 1, so 19. So I'm going to go to 19, and here I have my critical t-value of 2.093. So my critical value is 2.093. First thing I need to do is find my margin of error. So error is going to be our t-value times our standard deviation over the square root of n. So I have 2.093 times my standard deviation divided by the square root of 20. And I get 2,634.42. So I'm just going to go ahead and round that to a full dollar amount. So I have 2,634. Next, I'm going to construct my confidence interval. My confidence intervals are sample mean minus the error is less than our population mean, and our sample mean plus the error. So I have 9,004 minus 2,634, and I have 9,004 plus 2,634. So I get a 95% confidence interval that my true population mean is between 6,370 and 11,638. Thus, we found our confidence interval using the t-distribution. For problem 5, let's take a look at this problem. So, students randomly selected 30 people and measured the accuracy of their wristwatches, with positive errors representing watches that were ahead of time and negative errors representing watches that were behind in correct time. These 30 values had a sample mean of 117.3 seconds and a sample standard deviation of 185. We're going to use a 0.05 significance level test to test the claim that the population of all watches has a mean equal to 0. So, we're going to need to use a t-test for this, right? I already tell you that because it says to find the t-score. And we need to do that because our population standard deviation was not given. So let's go ahead and state our null and alternate hypothesis. Our null hypothesis is that there's no difference from the claimed value, right? So our mean equals 0. And my alternate hypothesis is that my mean doesn't equal 0. Because we are looking to test the claim that all watches have a mean equal to 0 seconds. And if it's not equal, then it's not equal to, right? We just need to prove that the mean is different. It doesn't matter if it's greater than or less than. So this gives us a two-tailed test. So when we look at our t-table, we're going to be using the critical t-value for the area in two tails. So what's the t-score for this sample mean? Well, remember that t equals our sample mean minus our population mean over our sample standard deviation over the square root of n. So I have 117.3 minus 0 over 185. That's kind of a high standard deviation over the square root of 30. And that gives me 3.479. So 3.479 is my t-score. That's my test statistic. Now, I need to know what my critical value for this test is. So I'm going to go ahead and write that my test statistic, my t-score that I found, is 3.479. So my critical value, I have a sample size of 30. So my degrees of freedom, it's going to be 30 minus 1, which is 29. So I go down to 29. Here we are. And I'm looking for the area in two tails. So I get a critical t-value of 2.045. Now, the t-test rules will be given to you guys on the bottom of the exam. They're also found on the bottom of the exam review. But I'm allowed to reject my null hypothesis if my critical value is less than my t-score. So I'm able to reject my H0 at the 0.05 significance level. So for problem 6, in a trial involving 6,002 children, only 14 of the 1,070 who received the vaccine developed the flu, compared with 95 of the 532 who got the placebo. So I'm going to use a 0.05 significance level to test for independence between the variable representing treatment and the variable representing flu. Oh, blue on blue, that's not good. There we go, flu. So I want to state my null and alternate hypothesis. My null hypothesis is that there is no relationship between the two variables. So there is no relationship between treatment and getting the flu. Our alternate hypothesis is that there is a relationship between treatment and getting the flu. And because we're looking at comparing two different variables here, we've got our lovely contingency table. We're going to be calculating a chi-squared statistic. So, first thing we want to do is find the value of a chi-squared statistic. You will be given this table on the exam, okay? So, to find the value of the chi-squared statistic, we need to fill in these areas. The first thing I like to do is come up with the total. So the total was that 1,602 people were participating in this study. I have that 170 over here. I have 532. What I'm doing is I'm adding up the sums of the rows, and I'm going to add up the sums of the columns. So I've got 109. I've got 1,493. I think I did that right. I did. Good job. Okay, so let's go ahead and fill this in this table. We should probably switch to something that's not blue because my table's blue. So I take my observed value. So if you got the vaccine and the flu, that's 14. Vaccine and no flu, that's a typo, is 1,056. Placebo and flu, 95. Placebo and no flu, 437. This is going to add up to our total number of 1,602. The next thing we need to calculate is our expected value. Friendly reminder, our expected value is our row total times our column total divided by our grand total. So for our first one, I'm going to demonstrate for vaccine and flu. So I take my row total, which is 109, times my column total, I take my row total, which is 1,070. I'm going to do that over here. 1,070, that's my row total, times my column total, which is 109. I divide that by my total, grand total of participants in this study, which is 1,602, and I get an expected value of 72.8. So I'm going to have to do this for every single one of these 4 squares in our 2x2 table. So I get 72.8, I get 997.2, I get 336.2, and I get 495.8. This is also going to add up to the total number of participants in our study. Next, I take my observed value minus my expected value. That gives me negative 58.8, 58.8, 58.8, and negative 58.8, right? This column is always going to add up to 0, okay? This total column is always going to add up to 0. These are always going to be the same number, except some are going to be negative, 2 are negative, and 2 are positive. I'm going to square this number now, because I need to find our observed minus our error expected squared. That gives me 3,457.44. And because all of these are the same number when I square them, I'm going to get the exact same thing. Now, last step, I take my observed minus expected value squared divided by the expected value. I'm going to get 47.5, 3.5, 95.5, and 6.97. That gives me a sum of, I didn't write it down. Okay, that gives me a sum of 153.47. Okay, this is my chi-squared statistic. Next, I need to find the critical value of my chi-squared statistic. Okay, I find the critical value using a chi-squared table. Okay, so I have a 2x2 table. I'm looking at the 0.05 significance level, so my critical value is 3.841. And the instructions of how to use a chi-squared table are right in the title. I reject my H0 only if my chi-squared statistic that I calculated is greater than the critical value. So my critical value is 3.841. So I want to state my conclusion about the claim, okay? So using our significance level, 0.05, we can state the claim about our test, right? Because 153.47 is greater than 3.841, we can reject our H0 at the 0.05 significance level. And this is the same question. All right, problem 7. Again, uses a chi-squared table. This one's a little bit simple for you. You don't have to fill out the whole table. So consider the following data from a study of high school students at least 16 years of age. Assuming that we want to use a 0.05 significance level to test the claim of independence between texting while driving and driving while drinking alcohol. So what are the null and alternate hypotheses for our study? So our null hypothesis is that there is no relationship between the variables. And our alternate hypothesis is that there is a relationship. Now it wants me to find the expected frequency for this cell right here. So I'm going to find that the total number of people participating in this study is 8,505 by adding up all these squares. My expected value is my row total times my column total divided by the grand total. So I'm going to take my row, which is 731 plus 3,054, times my column, which is 731 plus 156, divided by our grand total, and I'm going to get 394.7. So I just found the expected value for this table. The last thing this problem asks us is what's the critical value for this table. So because I have a 2 by 2 table and I want to look at a 0.05 significance level, my critical value is 3.841. The last question on our exam covers ANOVA testing. So the vertical semi-restrained test was used to conduct flammability tests of children's sleepwear. So pieces of fabric were burned under controlled conditions. After the burning stopped, the length of the charred portion was measured and recorded. The same fabric samples were tested at 5 different laboratories. The analysis of various results are as shown, right? They were calculated and given to us. So what's my null and alternate hypothesis? So my null hypothesis is that there's no difference in the mean burn lengths in the 5 different laboratories. So we had 5 different laboratories. I skipped 4. My alternate hypothesis is that at least one of the means, this is a equal sign. My null hypothesis is that at least one of the means is different. So they do not all equal each other. Or you can write at least one of the means is different. We need to identify the p-value. This is not something we calculate. This is something that's given to us. So we go and we see here, aha, our p-value, probably of this occurring by chance, is 0.031. That's our p-value. For C, I want to know, is there sufficient evidence to support the claim that the means for the different laboratories are not all the same at the 0.05 significance level? The answer is yes. Because our p-value is less than our significance level, we can reject H0 at the 0.05 significance level. All right, class, that covers our entire exam review. Remember, if you have any questions, please, please, please reach out to me. And remember that, hint, hint, wink, wink, our exam is going to be incredibly similar to this review. So as long as you are able to solve the problems on this exam review, you're going to do just fine.